Hi, I'm Nikolai from DeTectUs, and I'm going to give you our technical pitch about the workings of a surface plasmon resonance system using our own custom-built setup. So why use surface plasmon resonance? It is a label-free technique that requires no sample preparation and are thus suited for easy point-of-care diagnostics. It is sensitive in the nanomolar range, and that is the clinically relevant range for therapeutic drug monitoring of adalimumab. It is quick in assay time and takes seconds to minutes and requires only a few microliters of sample consumption. So since the beginning, we have built our own surface plasmon resonance setup from scratch with an optimized lens configuration. We have built the mechanical holder you see here that is mechanically stable so that we can do these measurements. We have also fabricated chips using cleanroom techniques and functionalized them with a peptide we have designed by ourselves. We have also designed the electronics ourselves and built them tailor-made to this specific purpose. So how does it work? This is an overview of the surface plasmon resonance setup using the Kretschmann configuration. You have a laser going in through lenses and a prism which excites surface plasmons on top, and surface plasmons are electromagnetic waves on a metal dielectric interface. These waves are affected by whatever is on top of the metal, which in our case are biological molecules. So zooming in to the biological recognition, we have designed our own peptides through the use of bioinformatics simulations, and so that it mimics the sites of interaction between adalimumab and TNF-alpha. We have linked this peptide to the gold surface through linker molecules and subsequently blocked them to avoid unspecific binding of plasma ingredients. We found that the peptide had nanomolar affinity towards the drug and that both the peptide and the linker molecules were unresponsive to plasma. So when the light beam comes in and excites the plasmon, it absorbs a lot of light, while the rest of the laser beam is being reflected. As the laser beam is being focused, it results in a spectrum of angles, which gives rise to this dark line in the beam spot. The dark line depends on the sharpness and thickness of the dark line depends on what lenses you're using. And we have optimized them to get the best results. So when the plasmon wave is created, it propagates along the surface of the metal, and it can only be resonantly excited if the momentum of the incoming light matches that of the plasmons. And that is why it's called surface plasmon resonance and why we require a very specific angles for this excitation. So depending on what is on top of the surface, different angles will be required. Thus, by detecting the change in the placement of the dark line, we can detect the change in what is on top of the surface, in other words, adalimumab. We have employed a 1D CCD camera to alleviate large data transfer rates, and that results in faster computations. It also helps with the size, decreasing the size of the electronics, and does an automatic integration of the signal. To further improve the signal, we have employed an onboard analog low-pass filter and a digital algorithm-based filter to improve the signal. In conjunction with the mechanical holder that is precisely and manufactured with precision and stability in mind, we are able to do fast and precise measurements with our setup. So all these points have made us able to build our own custom-made surface plasmon resonance system. Thank you for your attention.
So thank you. Are there any questions? Yeah.
So thank you for the presentation. So I like that you use peptide mimics that can bind to the antibody. So I have two questions. The first one is that you mentioned you block for non-specific interaction. How did you block for non-specific interactions?
With etanolamine, as far as I can recall. Yep.
And did you verify how much background signal you get after that blocking step from just plasma without adalimumab?
We did a baseline measurement as soon as we placed the drop, and
Okay.
use that as a reference.
Okay.
And then for the plasma case, we saw that it gave a negative response, but it was basically zero.
And so you use a laser, and so the last slide you've shown, there's a fair amount of fringes that occurs. So have you considered other light sources that could remove those fringes instead of using an algorithm to filter that?
We haven't really gone into those considerations
Okay.
at this point.
Probably using an LED with a bandpass filter would remove all of that.
Yes.
Because the laser will have a lot of fringes, of course, but
Yeah.
not a LED, which would be an incoherent light source.
But I think the low-pass filter should take care of the frequencies of, hopefully.
Yeah, you
Is
have
it-
to use a bandpass
Okay.
filter for the wavelength you want, but
Yes.
you should remove that.
Okay,
Yeah.
thank you.
Thank you very much. Interesting presentation. What I like is the fact that you don't use a kind of sandwich principle in order to detect adalimumab, in which both branches of the antibody need to be free, because patients can develop antibodies to adalimumab sometimes, in which one of the branches is bound to another antibody. Do you know whether that might affect your signal if you have one of the branches of one of the arms of adalimumab bound to an antibody? Does it matter?
We haven't tested that yet, so
Okay.
I don't
Okay,
know.
you don't know. But in general, with the surface plasmon resonance, is there a change in signal depending on the size of the molecule that you bind?
Yes, so the plasmon wave evanescently goes out into the medium.
Yeah.
So it's strongest at first, and it gets most affected by the size of the bigger the size of the molecule,
Yeah.
because they will give a larger increase in the refractive index on
Okay.
top of the media.
So in theory, you might find a different signal if something like that would happen.
Yes.
Yeah. Okay. Okay. Oh, thank you.
A brief question about the detection. If you look at the picture of the CCD camera, you see the width of the the figure, the black band.
Yeah.
Do you think you will get enough sensitivity to have a reliable measurement in the end? And what do you expect about future potential of improving the width of the signal?
So these are not to scale; they're much smaller in pixel line.
So
pixel density.
So if I look at this picture, it's the width is not the width you normally measure. So I see now a bandwidth. So it's the height basically of the black
Yeah.
band. So the picture is not the accurate, not the same result as you have. That's what you say.
No, the round image, that's our signal.
The
But-
round image.
Yes, and also these ones. So the overlay of the pixels.
Okay, so let us have a discussion afterwards.
Okay. Yes.
Yeah, I'm don't understand it yet, but I hope I
Sorry.
will later. Yeah.
Thank you very much for your presentation. It's very impressive that you built your SVR from scratch,
Thank you.
of course. So I was wondering, of course, these are usually inherently very expensive instruments, starting from Biacore till now. So how do you, just a rough estimate of the expected cost of this prototype that you have built, and with regard to accuracy compared to large scale or larger instruments, how do you?
So I think it's around 500 to 1,000 euros for to build the system,
This okay.
and then we just deposit gold on a glass surface, and that comes out to about with the reagents, I think around 20-30 kronos per chips, or
Okay.
it's 5-7 euros per chip.
That's right.
Can you repeat the second question?
The accuracy,
Yeah.
the accuracy of this compared to large scale ones.
I think what we actually saw, in the end we To detect the affinity of the molecule, we used a biocore instrument in a pure buffer. And when going to a plasma, it messed up our sample or the signal completely. We couldn't really do reliable measurements using the commercial one. But we saw that, and maybe it's because of that we're not using a dextran matrix, but we saw that the plasmons were, the measurements were unresponsible to plasma in like over an average of chips and measurements.
Okay, I also appreciate the effort you did to build an SPI instrument. There are also many on the market, and it's good that you have some approach which is much cheaper. But you know, for the target for sensors here, so you want to put it on a point of care. So is there potential to miniaturize, or how large it is? Can it be smaller? So can it be like this?
Yes, right now our system is rather big, but that is because it's not like the final iteration. For the detection of plasma, you have like a very specific angle, and you take the small changes, so we could lock the angle at like at that exact position, which would give the whole setup a smaller size. We haven't gotten into much development of the like a fluidic chip. We're currently just using a stationary pipetting, but we could manufacture and have ideas for like putting the droplet on and like making a small flow or shaking it or something like that.
Okay. Yeah, so no matter what you have in the end, it should be an enclosed box with some push button. And the inner part,
Definitely.
if this is technically fine, that's okay.
Yeah.
But
And if you really optimize the lens setup, I think you can make it so that the light is focused and bent in a smaller dimension.
okay.
So last question from Stefano.
Thanks for the presentation. I like the idea of using the peptide. I wanted to ask a couple of quick questions. First, how did you measure the strength? Can you tell us how you measure the strength and the selectivity of the peptide as you were developing it?
We used an ELISA assay initially to test different peptides compared to TNF-alpha. And then we chose the one that has the highest response in an ELISA signal. And then we went to the commercial system and generated a concentration curve, and like from the systems, the biocore systems, integrated the software, calculated the KD value.
Okay. And second, I presume that because it's a small peptide, the density of the peptide on the self-assembled monolayer will be important in determining the binding of the antibody. How do you guys determine the density of the peptide, and how do you make sure that that density is reproducible from sample to sample, from wafer to wafer?
We have employed a fluorescent tag to see the uniformity of the peptides.
How does that work?
So we attach the fluorescent tag on the peptide, and then that attaches to the surface, and then we see that, like as one from our team says, like a beautiful night sky of stars.
The peptide has only one lysine for the mobilization on the monolayer. I presume you use amino chemistry, right?
I would direct that answer to Sarah, because she's designed the peptide.
Okay, last answer, because we have to move on.
Hi, I'm Sarah. For the first part, we try to homogenize as much as possible. We know we had a very small amount of that, but we try to, by shaking and increasing the amount of the fluid to do it. And because we were using lysine for interaction of that one, and it's a specific tiles that we are going to attack to it to increase the possibility of homogenizing and decrease the. But we know that there are some spots there, but somehow it was helping for us because we needed a triple TNF to expose the maximum conformation that we needed for interaction. So kind of it helped us.